So good afternoon, everyone. Today we are resuming our activity, our seminar activity after the summer break and the SEA from last week. Today we have Martín López Corredoira for this Tuesday meeting. We apologize for the slight inconveniences we had. We are having some problem with the Zoom link. There will be a Zoom link shared with the Institute right now. And then this talk is going to be recorded and will be eventually uploaded to the YouTube website of the IAC. So today, Martín López Corredoira will be talking about fundamental ideas in cosmology. So Martín, you know, you have like 45 minutes and then we leave like 15 minutes or so for discussion. Okay, thank you.
Thank you very much. This seminar, I'm going to do a short introduction of the contents of this book that I have just published, an academic book on cosmology. Of course, in 50 minutes, I have no time to tell everything, but just to give a rough idea of the contents, and if somebody is interested, can have a look at the book. This book tries to fill some gaps in many books of academic books of cosmology, focusing more in the problems of the standard model rather than in the successes, and also describing some alternative ideas, talking about sociological problems within our science, philosophical views, etc. So I'm not going to describe what is the standard model of cosmology. I think most of you know the Lambda-CDM. The information is available in many books. We have a model of cosmology, but we are not unique in the history of science in having models of cosmology. All civilizations and in any epoch have some representation of the cosmos they know. For instance, here I have put just as one of the multiple examples, the representation of the cosmos in the Middle Age in our Western civilization was okay, you should. Okay, no problem. In the Middle Age, for instance, in the Divine Comedy by Dante, the representation of the known universe in the epoch was something like this, with the Earth and the planets and the sun and the moon all around the Earth. And then there was a ninth sphere with the fixed stars. And plus, in the end, we have something here, which is the primum mobile, the concept of primum mobile, which was the source of all motions of the planetary motions. Nowadays, we have something very different, but with some similarities. Bruno Minghelli, the astronomer Bruno Minghelli from Switzerland, has remarked some curious similarities between the Middle Age model and our present-day model of cosmology, in which here we have the Earth or the Sun. We are here, have many layers. In the end of these layers, we have the Big Bang, the big explosion, which is is in some way equivalent to the primum mobile of the Middle Age. Bruno Minghelli thinks that this is more than a coincidence. He thinks that indeed, when we are doing cosmology, we are doing some psychology, some symbolic expression of the states of our mind. So it has something to do with some subjective approach rather than the objective observation of the cosmos. This is, of course, discussable anyway. No doubt that we have a possible representation of the cosmos. The question is whether we have the final answer to what is the universe. All civilizations have thought to have reached the final representations of the universe, but this is not objective from a historical point of view. And we don't need to be philosophers or historians of science just to realize that we are living one moment which is special in some aspects, but must be maybe it's not the final moment of the creation of the cosmology. For instance, the Narlikar, giant Narlikar, the cosmologist, says that there is one trait which the cosmologists of all seem to share with their modern counterparts. Their fond wish that the mystery of the nature of the universe will be solved in their lifetime. Also, Mike Disney, astrophysicist, still living nowadays, calls it the fortunate epoch assumption, the idea that we live in a first human epoch that possesses the technical means to tease out the crucial observations. Certainly, perhaps there are many optimistic researchers that think that we are close to find the final answers of the cosmology when this question of cosmology has been the question for many centuries or millennia, and possibly we are not the last to make this question. It's true that our standard model is making impressive, successful predictions, and we can check these predictions with the standard model, but this happens many times throughout the history of science. The society, our society is very impressive by this capacity of the physicists to make successful predictions. Here, for instance, I remark 3 moments of the history of science in which there was a big leap, a big step in our knowledge, in our progress of our science. The first one is with Tales of Miletus. I put here the 6th century before Christus, which was more or less coincident with the origin of the science in the Western civilization, and also the rational philosophy, more or less. And this moment is one in which Tales of Miletus puts the first prediction of a solar eclipse in that time. Another special moment with extraordinary prediction came with Isaac Newton, for instance. I'm putting just 3 examples. There are plenty, there are hundreds of examples, but these are just 3 remarkable examples. As Isaac Newton, not only with the theory, the physics of Newton, but also with the gravitation. And the moment in which Isaac Newton became something gloriously vindicated in the intellectual community, not only in the science, but in the society in general, was when some predictions were confirmed. For instance, when Edmund Halley confirmed or predicted the arrival of some comet with his name at some epoch, and this was confirmed. This was the people in those times, in 18th century, was impressed by the capacity of a theory, an abstract theory like Newton, to predict how the heaven moves. A third example can be given with Albert Einstein and the general relativity. Of course, we know how important is general relativity, but the society became more convinced of this theory after the predictions were confirmed by Eddington and the co-workers. As I say here, in all these cases, the society has the impression that physicists could manipulate gravity equations to foretell how the heavens move. And this is something sociologically speaking, historically speaking, comparable to what the magicians or the prophets were doing in the primitive society or in other religions. So the role of these scientists, the sociological role, although of course I agree that science and religion is something totally different, but the role is becoming something very different. And particularly in cosmology, which touches one of the questions which is important for the humanity for a long time. Yes, please. Einstein. Yes, well, I'm referring to Einstein. Maybe I have taken for somewhere else. Yes, 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 it's just a metaphor. It's not a religious messiah. But well, in the book, I have a long explanation on how was the process between Newton and Einstein. The problem of Newton is that he tries to create a cosmology, but there was some failure. Everybody knows the stability or the collapse of due to the Newtonian gravity. And it was expected a new change in gravity just to start the new era of cosmology. Einstein put forward this change. So it was something like the society was expecting somebody that solved this problem, and suddenly the emergence of cosmology came immediately. Indeed, 2 years after the general relativity, Einstein himself published the first paper on cosmology. So this shows how eager was the society to create a consistent, a coherent model of cosmology in that time. Well, no, well, here I refer to the Eddington, the deflection of the light predicted by Einstein, which was perhaps the most remarkable prediction. Of course, the Mercury periodium was also remarkable, but for the society, the question is why people became so interested in Einstein and the general relativity. And, because people does not know so much tensors and mathematics, they are not interested, but they are impressed when an astronomer could measure a number that was predicted a priori by a theoretician. This was the moment in which Einstein became a iconic hero of the society, in 1919. After the general, yes, after. No. I was saying that before Einstein, there was some expectations to do some progress in gravitation, because with Newton alone, we could not create a cosmology. So in the moment in which Einstein said, okay, I have the solution, I can produce a cosmology because I have a solution for the collapse of the universe. I have a gravity theory that can contemplate all the universe that we have. This was the moment of the creation of the modern cosmology. And this moment, there are some reasons, I have no time to discuss, but there are some reasons to think that it was somewhat expected. In the 19th century, there were some hints in this direction. Nothing to do with the predictions of Einstein. I mean the eager to create something cosmological, also related with the mathematical models, the new geometry, the new mathematical geometry that created Riemann and these people. So the atmosphere was created for the creation of a cosmology, but something was failing, was the gravitation. So came Einstein and put the element that we need, and this triggered the starting of the history of modern cosmology. This is what I wanted to say. I'm sorry that I have not much time, otherwise I will not finish on time, but surely we can discuss later whatever you want. Well, undoubtedly, general relativity is one of the fundamental pieces of modern cosmology. The second important piece is the extragalactic astronomy. That was clear, the scenario that we have many galaxies, not only the Milky Way, since only 1 century ago, after the Great Debate. These two elements constitute the initial period of the cosmology, the Great Debate, and the cosmological models derived from general relativity created by Friedman, Lemaitre, and others. There was a second epoch of cosmology when it was compared with some observational data, particularly with the redshift of the galaxies explained by the expansion, as Lemaitre and Hubble said. And also the first ideas, the first theory of creation of helium that were produced in the end of the 20s, beginning of the 30s by Suzuki and Lemaitre, for instance. There was a third epoch after the Second World War with Gamow and collaborators mainly, in which he could make some predictions of the light elements. And moreover, he makes predictions of the existence of Cmb, which was successfully confirmed and interpreted in cosmological terms in 1965, I don't know. After that, we have a period of acceptance and a period of enlargement in cosmology, in which we have to incorporate elements to understand the evolution of the galaxies, the early universe models, and also we have to explain some facts that were not explained a priori by the model. So indeed, the model by Gamow was making some predictions that were later confirmed to be wrong. The predictions were wrong. So one has to add ad hoc some elements in order to save the theory. This happened with the grand unified theory, for instance, to understand why there is a asymmetry between matter and antimatter, the non-barionic dark matter, the inflation and dark energy that I will refer later. And finally, according to some historians of science, for instance, I'm following Luminet as this division, there is a sixth period, the period in which we are living, which is the period of high precision cosmology. After the 1998, more or less, which was the moment in which it was established the Lambda-CDM as the standard model, including the acceleration of the expansion. This period is characterized by a lack of discussion of the fundamentals of cosmology. Most of the cosmologists, the standard cosmologists, I mean the orthodox cosmologists, are not interested to discuss the fundamental ideas, either the expansion, the origin of the Cmb, or whether the dark matter or dark energy exists. They assume, of course, that these elements exist, and the inflation and so on. Now they are discussing in measuring with higher accuracy some parameters, and making some debates about some subtleties of the model, something like the equation of the state of the dark energy, or the types of inflation, or the number of neutrino families, whether the dark matter is hot or cold, subtleties. This, in my opinion, and this is my impression, no, this has some parallelism with the Byzantine epoch in the late Middle Age. It was an epoch in which people were not discussing about the existence of God, of the cherubs or the angels. They assumed, of course, that Jesus was existing and all this stuff. They were more interested in subtleties, so like the sex of the angels, or how many angels are able to fit within a needle head, for instance. This is what we call Byzantine arguments. Byzantine because it comes from Byzantium, the empire, or in the East, the Christian East, Byzantium, in the late Middle Age. Today, we are doing something similar in some sense. We are forgetting about the fundamental questions, which are not totally clear, as I will show in the following slides, and we are paying too much attention to minor subtleties. And the problem is that when we have better instruments and we are trying to make higher precision cosmology, we are increasing the number of tensions. The higher the precision with which we try to measure all the parameters and all the different predictions, we find more and more tensions with the model. So my idea is that perhaps we are going too fast in the development of cosmology, and we have to pay more attention still to the fundamentals of the cosmology, the basic ideas. Even the last elements that have been added ad hoc, I insist, in order to save the theory, the CP violation, the inflation, the non-barionic dark matter and dark energy, what I call the 4 dark nights. The CP violation was introduced in the 70s in order to explain what is evident. We don't see antimatter in the universe. So this means that there should be a violation of the shared conjugation and parity reversal. This is abbreviated the CP, symmetry of the fundamental particles. The problem is that if we accept this violation, there is a prediction that the proton should have a finite lifetime. So far, up to 2 years ago, we have not found any decay of the protons, and there were many experiments trying to measure it. The actual limit is in 10 up to 34 years, the minimum time of the life of the proton, which is quite a lot. Still, of course, there is some debate whether it can be found with higher lifetime, but it looks that it is not clear that this element added at all is working properly. The other element, as I mentioned, sorry, was the inflation. I'm not going to tell why the inflation is necessary. Maybe many of you know, to solve the problem of the homogeneity of the universe, the correlation in the Cmb of distant points, etc. The fact is that we have around 1,000 different models of inflation. Inflation is such a flexible theory that can predict practically everything. Everything that you can observe, you can create a new model of inflation that can fit the data. So a theory that can predict everything is a theory that predicts nothing. So we have not any direct proof without any doubt that the inflation is there. Of course, with inflation, we can explain many data, and apparently some data are more in favor of inflation than not, but it's not a direct evidence. At present, it's just a hypothesis. There are also some data that at least disprove some of the most common types of inflation. For instance, it is predicted that we should have some correlation, some positive or negative correlation. We see here at a large scale angles in the power spectrum of the Cmb. And the fact is that we don't see any correlation. This was indicated as a sign that possibly, at least the most basic ideas of inflation are not working correctly. Possibly there are some exotic models of inflation that work, but not the most direct ways. Cmb is also related with the other two ad hoc elements, the dark matter, the non-Barionic dark matter, and the dark energy. We have to remember that in the 60s, end of the 60s and the beginning of the 70s, it was predicted the amplitude of the anisotropies of the Cmb, and they should be 100th or 1,000th of the temperature. This was later realized that it was incorrect in the 70s, and only until the 90s was not found that some anisotropy, and was in a much lower level in 10⁻⁵ with COVID data. This forced the cosmologists to introduce some new element, which was called non-Barionic dark matter. We need the non-Barionic dark matter in order to save the theory. This was not a prediction of the model, it was something to save the theory. Something similar can be observed about the emergence of the dark energy. In the 90s, at the beginning of the 90s, the favorite cosmological model included only omega matter with a value around 0.2. However, the first data of the power spectrum with the multipoles of the Cmb have shown this first prominent peak. You can see here at multipole 200, which is directly related with our omega total equal 1. So omega total equal 0.2 could not work. We need something else. And this justifies the necessity of dark energy. Of course, you will say it's not only the Cmb, there are more evidences. It's true, there are more arguments. For instance, for the dark matter, we know that it was motivated also, not the non-Barionic, but at least some matter which is dark, either baryonic or non-baryonic, is motivated by the rotation curves of our galaxies, by the clusters of galaxies, even in the theory, in order to explain the stability of galactic disks. There are other explanations nowadays for the stability of galactic disks, but in the 70s, it was thought that it was totally necessary. There are also, at least in galactic scales, many problems without a clear solution related with the dark matter, with the halos of dark matter, the problem of the casket halo, the problem of the angular momentum in galaxies, the problem that all the satellites of the galaxies are in a plane instead of spherically distributed. Certainly, I agree. There is a lot of discussion still nowadays about that, and people think that they can solve these problems, but it's not a general consensus, not a general agreement. It's still, dark matter has some problems and are being discussed. And the major problem is that after many experiments trying to find the particles composing the dark matter, the non-Barionic dark matter, nothing was found in the last 30 or 40 years. No WIMPs, no actions. There is no any direct, undiscussable evidence about some particle of the dark matter. They are still, of course, trying to find it. It's still in progress, the research. About the dark energy, I said that the CMB was part of the motivations. There were other motivations too. There are at least two other important motivations. One was the age of the universe. Without the dark energy, the age of the universe will be less than 10 gigayears, and this does not fit the oldest objects that we know. And perhaps the most popular, the most important observation that triggered the necessity of the dark energy was the supernova Hubble diagram, with the research by Rees et al. And Perlmutter et al. In the 1998. It is well known that these supernova that are supposed to be standard candles, the fact that they are a little bit fainter, only 0.2, 0.3 magnitudes up to redshift 1, the fact that they are a little bit fainter can be explained in many other ways. We don't need to introduce dark energy to explain the Hubble diagram. Of course, the most direct idea that we can have is the extinction, either intergalactic extinction or the extinction in their own galaxy with very extinction. But there are other ideas. For me, one of the most impressive arguments in the literature, I'm not talking about my research, but which I'm quite convinced that is important, is the analysis of the possible variation of the luminosity of the supernova. We believe that the supernova are standard candles. And we think that the supernova at redshift 1 or redshift 2 have the same luminosity than the supernova here. Of course, there are theoretical studies and so on, but it's not so clear. Here, for instance, I show some paper by Lee et al., some group from South Korea, in which they show a clear correlation between the Hubble residual, that is the excess of magnitude with respect to the cosmological prediction, and the age of the host galaxy. And there is a quite clear correlation. Apparently, the supernova, which are in younger objects, this is in the local universe, I mean. This study is analysis in the local universe, so there is no discussion here about cosmology. When we have young objects, we have some excess of Hubble residual. This apparently, as far as I understand, is pointing that there is an evolution of the luminosity of the supernova. It's not so standard candle as we believe. But, well, it's not my work. This is being discussed nowadays. I'm worried, however, that this paper, for instance, published in Astrophysical Journal, has only 8 citations in 2 or 3 years. So apparently the community is not interested in these kinds of results for some reason. The community is interested just in making bigger and bigger the dark cosmology community, investing more money in experiments for the dark energy search and dark matter. Of course, and is very well have been very well recognized in the last 24 years, including the Nobel Prize in the 2011 for the discovery of the accelerating expansion of the universe. Well, this is a hypothesis, not a discovery yet, I would say, but the Nobel Committee thinks there is a definitive proof. Summing up this first part, I think we have introduced many elements which are highly speculative in cosmology in the last years. And we have introduced it because we need them to save the theory. Even the most basic aspects of the cosmology can be discussed. We should not be afraid of discussing fundamental ideas in cosmology. The most fundamental aspect is the expansion of the universe. We know, of course, that most of the cosmologists, even myself, are more in agreement with expansion. I'm more convinced that there is expansion than the static models. But however, are we 100% sure of that? Hubble himself, one of the discoverers of the Hubble law, expressed some doubts throughout his life. Here, for instance, I have a quotation in 1947. He said, "It seems likely that redshifts may not be due to an expanding universe, and much of the speculation on the structure of the universe may require re-examination," said Hubble himself. It is well known that in the same year in which Hubble proposed the explanation of the expansion of the universe for the redshifts, other ideas appeared, particularly Zwicky proposed the Tyrant light hypothesis, in which the photons emitted by the galaxies at high redshift were interactive with some matter in the intergalactic medium and producing the loss of energy that gives place to the redshift. There is plenty of discussions about that. You can imagine in the last 90 years, there are tens or hundreds of papers discussing this question. The most important problem of the Tyrant light that was discussed a long time ago is that we don't know any kinds of interaction between photons and particles that do not change the direction of the photon. So all the scattering that we know changes the direction. And if it changes the direction of the photon, this produces some blurring of the images which are farther away we don't observe. Also some possible dependence on the frequency. But there are exotic proposals with exotic physics trying to solve these questions. So there is literature about that, at least from the theoretical point of view. So from the theoretical point of view, we cannot be 100% sure that the redshift means expansion. No, there are many other theories to explain the redshift. Just have this idea in mind. From the observational point of view, do we have a direct evidence of the expansion? The answer is no. There is no any direct evidence. The only direct evidence of expansion will be that we see some galaxy that is moving away from us and is changing the distance. But in order to see this, we will need millions of years of observations, because in few years we cannot appreciate this small variation. The only thing that we have is indirect tests of the expansion. And some of them, of course, do agree with the predictions of an expanding universe. I have no time to describe all the tests of the expansion of the universe. Just to put one example, one which is, in my opinion, one of the most impressive one and the most successful confirmation of a prediction is the measurement of the Cmb temperature. The prediction of the standard model says that it should be with a factor 1 plus set. So the universe is more dense in the past, the radiation is more dense, and is hotter in the past in some way. And this has been confirmed even at least in two independent ways. One with the temperature obtained with excitation ratios in atoms and molecules by absorption lines observed in galaxies at a high redshift. And the other with the Sanchez-Seldovich in clusters of galaxies in the interaction with the Cmb. And both of them agree that the prediction of the expanding universe, so this is a quite successful point in favor of the expansion. We have to bear in mind that, however, that this is not totally 100% sure to disprove the static universe. First of all, because we don't have a Cmb theory in static universes, so we don't know whether we can produce Cmb in a static universe so far. I will talk about this later. There are also curious cases of the opposite thing. For instance, if you think in a naive way, the most simple idea of space is a static Euclidean universe without expansion, as I said. In this universe, you will expect that the objects of the same size, of the same linear size, will decrease the angular size proportional to the distance. So the angular size is inversely proportional to the distance. Since the distance is proportional to the redshift in these models, the angular size will be inversely proportional to the redshift. And this, maybe by chance or just because something else, is curiously is what is observed in objects that are believed to have some similar size in radio galaxies and quasars, and also in galaxies invisible. However, the standard model predicts something very different, as we see here. The angular size is not inversely proportional to the size. Of course, you say this does not mean that we cannot confirm the expansion. The only thing that it means is that we have evolution of the galaxy size. This is the official interpretation. This has other problems because this will mean that if we go to redshift 5, the size of the galaxies, average size of the galaxies, the elliptical galaxies, is like 10 times smaller than at present time. It's too much density. So this creates another problem. So how to explain this strong evolution? But for sure, if we think that the cosmology is correct, there are some other ways to save the theory just with the evolution. In principle, as I said, I'm not going to put my hand in the fire that the universe is in expansion. You can put your hands if you want, but I'm more in favor. At present, I'm more convinced by the expansion than the opposite. Right. About the CMB, this is a second observational pillar of cosmology. We know that it has been very successful in the last years for the making predictions and fitting something apparently complex like the power spectrum with a model with only 6 free parameters. Also with the polarization, more recent data, and other things. I'm not going to enter in detail. Well, it's impressive, but not so much. We have to bear in mind that all the peaks of a power spectrum that we see here are not independent. When we do the Fourier transform or the legendary transform of this power spectrum, we recover the 2-point correlation function, which is a function which is much smoother. There's only some abrupt transition, some non-continuous first derivative here, but for the rest, it's a smooth function. And mathematically speaking, I'm not talking here about physics, mathematically speaking, it's not so complicated to fit a function like this with 6 free parameters. And even with the real data here, this is just a toy model, but if we use real data, we can invent a mathematical model to fit with 6 free parameters, roughly, not as perfectly as in the standard model, but roughly all the peaks of the CMB. Indeed, there are some literature with, and now I talk about physics, that try to fit the power spectrum with alternative cosmologies. For instance, the quasi-steady state cosmology. I will explain later what it is. It's an alternative cosmology, nothing to do with Big Bang. Or with introducing MOND instead of Newtonian theory, a modification of gravity with spiral neutrinos, and also with 6 free parameters here in both cases. They can provide acceptable fits to the power spectrum. So I remark it's not as good as the standard model, but it's not terrible. They need further work, I think. But so if somebody asked me the question, are we sure that the CMB is a proof of the Big Bang and can only be explained with the Big Bang? I would say, well, I'm not so sure. Of course, the Big Bang make it fantastic. It's the best hypothesis that we have. We have to bear in mind that we have hundreds or thousands of people just making refinements in the theory just in order to make it work. But there are possibilities to make a fitting of the CMB with other ideas. Perhaps the major problem of the alternative ideas is one fundamental one, the black body radiation. The alternative cosmologists claim, of course, this can be produced with the thermalization of the radiation, but it's not so simple. We don't know any mechanism of thermalizing the radiation in such a perfect way. And if we include the integration along different redshifts, it's very difficult to maintain a black body. But the other aspects are possible to be worked. Moreover, CMB is not, the predictions of the standard model for the CMB are not perfect. There are many problems, tensions, observations that are not easily explainable within the standard models according to the literature. They are not my words. This is what I'm doing here, a review of the thing. For instance, there are many papers talking about the alignment of quadrupole and octopole, that there is no enough correlations at large scale. I have mentioned it before for the inflation, the asymmetry between ecliptic and hemispherical, the contamination, even after correction of the foregrounds of maps, there is still some imprints of contamination, off-parity correlation, etc. There are many topics, and all these topics have some significance to sigma, 3 sigma, 4 sigma, so they are not random fluctuations. According to the literature, there are some things here that are not totally understood. A third fundamental idea in cosmology is that the Big Bang is the only way to explain the abundance of the light elements. This was indeed the origin of the Big Bang theory with Gamow and even before Gamow. However, nowadays, with the recent data, it's not so clear anymore that the Big Bang is supported by the abundances. First, again, we have many alternative explanations for these abundances, with either with a population 3 stellar nucleosynthesis. Second, the methodology used by the cosmologists is not appropriate because they are trying to make predictions that can be tested by observations, and they, instead of predicting the value of parameters, they feed the parameters after the observations, which is not the best way to confirm a theory. But most importantly, and going to the data, is that nowadays there is only one element which more or less agrees the prediction of the Big Bang theory, and this is the helium-4. This agrees. Well, the price of it has also some free parameters. We have the baryonic density, which is also a problem, but with the present day model, there is no problem with the helium, or very minor problems. All the rest of elements are not useful to test anything. For the deuterium, nowadays, it is not understood the production and evolution mechanisms, so and can be confused with many other mechanisms of stellar nucleosynthesis, cosmic rays, etc. For the lithium, in principle, should be a good candidate for comparison with the cosmology. Should be in principle, theoretically. But what happens? That there is no agreement. There is the lithium problem that has been lasting for many tens of years already, at least 20 years. We know that there is a discrepancy of a factor 3 or 4. The abundance of lithium is 3 or 4 times lower than predicted. Ad hoc, cosmologists try to justify this agreement, and they introduce, well, possibly there is some degenerate, some destruction process, blah, blah, blah. But okay, if there is some degenerate with some process that have nothing to do with cosmology, lithium is not a bailiff anymore to confirm cosmology. And the same thing with beryllium. There is some degeneracy with stellar nucleosynthesis. So no element can be used except helium, and helium enough is only one parameter, which is not so success. Last, and I have, yes, a little of time. Last point, last pillar of the observational cosmology, I will say that is the formation and evolution of structures and galaxies. Something very close to our to the work that we are doing here. Well, of course, Cmb is also one part, but the galaxies are there, and we can make maps of the distribution of galaxies. So it's a quite direct observational data. It's true that, roughly speaking, or in a major description, the standard model can describe the details of the large-scale structure. However, we have to take into account two things. First, that there are other competing models. People do not know about these competing models because they don't care about the alternative ideas, but the quasi-steady state theory has produced also explanations for the large-scale structure. There are also the plasma cosmology is another cosmology that is different, and there are also explanations. They are not as good as the standard model, I agree. Possibly they are not as good, but they are as good as the first prediction of the standard models maybe 20 or 30 years ago. It's simply, they have not enough manpower to develop it more. Also with MOND, there are papers. This one was published very recently, for instance, the score is lofty. Here with the power spectrum of the galaxies. This is produced with MOND recently with the HCT, there are, etc. There are alternative ideas. So the fact that one model can fit some data does not mean that this model is correct, because maybe there are other alternative models that also fit the same data. No? This is the first thing we have to take into account in all the observations. The second point, again, I insist, the predictions are not perfect. And now that we live in the high precision cosmology, we are finding more and more tensions in between the data and the theory. I have no time to tell all of them. If somebody is interested, I give enough bibliography in the book. Here I give some examples. No, there are papers talking about the departures of isotropy and homogeneity. There are papers talking about big structures, walls, filaments, voids, or whatever, with underdensity or overdensity, which is very different from the predictions of the standard model. Here, for instance, I put the example of the KBC, the local KBC void, which, according to some calculations, is 6 sigma away from the predictions of the Lambda-CDM. There are periodicity of structures. There are streaming motions which are too big. For instance, here I find one paper, recent paper, talking about the cluster El Gordo, with some two subclusters at the high speed, and according to some calculations, they are not my calculations, but according to the authors, this is again a tension of 6 sigma, and some one and again. So there are many papers in the recent literature talking about 5, 4, 6 sigma tensions. If we sum all of them, I think we cannot say that our model works perfectly. And of course, we have the all problems that have been in the last years. Now, this year it has been the the discussion about of the James Webb images, and people is being amazed that we have so many galaxies at high redshift, well-formed galaxies. So this is something not expected a priori in the standard model, but this is something that was already remarked since at least 20 years ago. We have too many massive galaxies at high redshift, and the standard model of, including the standard model of a large scale formation with a downsizing scenario, has important problems to give explanation to this. Also to give explanation to the chemical composition, the dust, etc. I will say, summing up, that our model has many problems. I'm not nobody to say that the Big Bang is wrong or not. I don't know. But at least we have to recognize that it has many problems, and possibly we have to be a little bit less optimistic and say, maybe we have made some errors in our fundamental ideas. Those ideas that we have said 50 years ago that they are fixed, and we don't discuss anymore about this, maybe we have to revise some of these ideas. But as Landau, the Soviet Union physicist, said already 60 or 70 years ago, as Landau said, cosmologists are often in error, but never in doubt. It's very difficult to see a cosmologist to say, I was in error. They will add new elements, new ad hoc elements, just trying to save the theory, but recognizing that I made a mistake, very few. I have, especially from the standard cosmology, I mean. This is wrong methodologically from a point of view of philosophy of science, because as was said even in Sherlock Holmes novels by Conan Doyle, the fiction character, it is a capital mistake to theorize before you have all the evidence. And the major problem that we have with our cosmology is that we have put first the theory and then the confirmation. This is not the correct way to do the things. First, we have to understand the data and then building the theory. And if something was not correctly working the theory, start again the game, but don't insist in adding ad hoc elements more and more, because it's not the best way. Well, this is, yes. In 5 minutes, 5 minutes. Okay, 3 minutes, 4 minutes. I will work. Of course, I have no time to discuss many other things that are here. I want to say that there are alternative models, of course. Standard model is one of them. If we examine the literature, there are plenty of models. Some of the models are not so alternative.
Él pasa de todo. No sé si me va a ver mi mensaje.
Sí, vendrá y dirá,
Yes. Some of the so-called alternative ideas in cosmology are not so alternative. They are just small variations on the things that we already know from the standard model, just different types of inflation, varying the number of neutrino families, different equation of the states of the dark energy. I will not call this alternative cosmology. This is a standard cosmology with small variations. There are, however, some other more serious variations, which they preserve most of the aspects of the standard model of the Big Bang, but they introduce some big changes also. For instance, the idea of a fractal universe, that they claim that the universe is not homogeneous, but fractal at large scale, a very large scale. The idea of cold Big Bang, in which there is a Big Bang, there is expansion, but instead of a hot Big Bang with very large temperatures at the beginning, we have zero temperature at the beginning. The idea of variation of the constants of physics, or modifying the gravity, or using Friedman models, but with different parameters, not the Lambda-CDM, like the Milne or the HCT, cyclical universe. These are possible variations. And then we have more extreme cases, which has nothing to do with the standard model. They are not Big Bang. There is not a beginning of the universe. For instance, the quasi-steady state cosmology, the plasma cosmology, or even the most exotic cases, in the most extreme cases, people proposing static universes. I have no time to discuss many things. Quasi-steady state cosmology, well, it's a historical case developed by Hoyle and blah, blah, blah. The thing is that it can work very well for some aspects, but people decided to abandon it some years ago. And the plasma cosmology was also very important because it emphasizes that the electromagnetic forces are the most important force for the creation of galaxies and the large scale structure rather than the gravity. The gravity exists, of course, the gravity is always there, but apart from gravity, there is electromagnetic forces. I have no time to discuss all these things. The impression that many heterodox cosmologists have, Narlikar is one of them. Narlikar was one of the proposers of the quasi-steady state cosmology, is that nowadays cosmology is not dominated by scientific discussions, but dominated by some social dynamics. There is what is called a snowball effect arising from the social dynamics of research funding drove more researchers into the standard cosmology fold and contributed to the drying out of alternative ideas. It's very simple what it's saying. Everybody of you that are professional researchers know what they are talking about. There is no money, there is no students, there is no telescope time, there is no possibility to publish in important journals, there is no much conference or very little when you try to investigate exotic models of cosmology in comparison with the work in orthodox cosmologies. This does not mean that there are papers still of that, but certainly there is an important motivation of the people to do standard cosmology. And this is not how good is the model, it's the money. If you want to survive in the system, don't make alternative things. This is the message of our system. The idea is something like the following. If you have a higher success standard model, this will produce more scientists and more money dedicated to work with it. This will solve more problems ad hoc, and this will make the theory more successful until somebody realizes that maybe it's not the right way. But meanwhile, we will continue to add more ad hoc elements just to save the theory, etc. Well, I have no time to more things. Just to emphasize, I go to the last slide. In this book, I dedicate, let's say, 1/3 of the book to sociological and philosophical discussions, many of them by scientists, not only philosophers, but historians, philosophers of science. Just to remark that cosmology is a mixture of many things. Of course, we have the official cosmology here in the Research Institute, but there is also some interaction of the society with the scientists, and it's not totally independent, the research from the ideas in the society. So the religious ideas have some influence, at least have some influence in the beginning of the creation of the theories. The political ideas have influence, economic ideas have influence, everything has influence in something as speculative as cosmology. Maybe other fields of science are more objective and more robust, but cosmology is a field which is very connected with many worries of the society, so it is not independent of other ideas. Just to finish, and this is the last one, I want to put what is indeed my impression, but with the words of Jean-Claude Pecker, a heterodox cosmologist who died recently, 2 years ago, who said, and we will pretend to understand everything about cosmology which concerns the whole universe. We are not even ready to start to do that. All that we can do is to enter in the field of speculation. So far as I am concerned, I will not comment myself on any cosmological theory, on the so-called standard theory, less on many others. Actually, I would like to leave the door wide open. And this is the last slide. 10 seconds more, just to say that this is I said at the beginning, this is an academic book, more indicated for researchers, for students, postgraduate or undergraduate students of physics, and also of history of science. My interest here is to make a large review with a lot of reference. So I recommend to the persons who try to do some kinds of new research, at least as a source of reference. There are almost 1,000 references in this book that I think can be useful to many readers. And that's all that I have to say.
Thank you, Martin. So we'll have much.
Well, no, one second. Before somebody asked me, in the library of IAC, they are buying the thing, but it's not yet available. It will be in the near future. But if somebody is eager to read the book before it comes to the library, ask to me, please. Yes.
Thank you, Martin. So, okay, so have questions. I'll start with the questions from the room. People online, please type your questions in the chat.
I think there is a problem when we have these kind of presentations, which is quite polemic, that we just have essentially 1 minute for discussion. Well, having said that, there are so many things I
Yeah.
disagree in the presentation. So starting with the way you present the need for cosmology, I understand you mean a cosmological model of the evolution of the universe. And it was quite amazing that before observations supported the idea of an expanding universe by combining the cosmological principle of a homogeneous and isotropic universe on very large scales and general relativity, you end up with Friedmann equations also derived by Lemaitre, and you end up confirming Slipher, Hubble, and even Lemaitre's calculations, as we recently learned from monthly notices, right? So there was not a craving for a cosmological model as we can see in the history, but it's true that with Newtonian physics, you can derive a cosmological model. There's no problem for that. There is a problem to make it valid on very large scales. There's a problem to have a pressure term because you just get that from relativity, but you can have derive the Friedmann equations from Newtonian physics. Lambda-CDM as an integration constant in general relativity does not emerge in a natural way. You have to put it by hand. And that's actually something which is very interesting to make the exercise, because when you take Friedmann equations as derived from Newtonian mechanics and you don't have lambda and you don't have, you don't have lambda, then what you end up is having a problem with a static universe. You can't have a static universe. And that's so easy from A dot scale from the first and second Friedmann equation to see. So then you don't mention Albers paradox. Why don't we see a very shiny sky even during day? You need a finite universe and you need it to be finite in space and time. You can make the calculations and it's 10 light years. I've done the calculations myself. If you solve those Friedmann equations and you assume it's static from the very beginning and it's not 10 gigalight years as an order of magnitude as we have in our observable universe. You were mentioning Tyrant light, but you were not mentioning that we have, since it's true, it's quite new. Since 8 years, we're using routinely baryon acoustic oscillations as a standard ruler, which is not affected whatsoever by Tyrant light because it's not using luminosity distances. You were mentioning BO's Rokema 2015 as something alternative because it's dependent on the environment, but that was predicted with simulations 2013, and I pioneered the BO measurement from cosmic voids, which is anti-correlated to the one from galaxies, as we expect, because they are tracing underdensities instead of overdensities. You were mentioning the R equals CT model, which when you put it in, and you call it correctly Milne universe, because it's essentially an empty universe, unless you have that the density term is compensating exactly the lambda term, which is a fine-tuning of a model. So there are so many papers you're mentioning. Mont is not based on a fundamental theory, but dark matter is. We have the Peck-Sequin potential, we have the actions which emerge as a natural model for dark matter, the lightest supersymmetric particle, etc. We have models from theory which are predicting and consistent with something. And you mentioned Fritz Zwicky, who, by the way, coined the term dark energy based on the motions of galaxies in the Coma cluster. So I'm a little bit surprised the way you present the rest of scientists as magicians, and you relate them even to religious people by calling Messiah of gravity. I think it's not the correct perspective. And I miss more discussion, because we could go, if we would stop at each thing, I think we could go into the details, but yeah, just out of my head, that's what I can say.
Yes, I totally agree that this will be, all these topics will be for a very long discussion. First of all, I have to clarify, maybe it was not clear enough, that I do not agree all these ideas that I presented. I'm making a review of ideas which are in the literature. Just to mention, for instance, at the beginning, when you say, no, there are no models consistent with being static. Well, I'm not an expert theoretical cosmologist trying to do that, but there are papers by professional experts in general relativity that try to solve all the problems with the we can, but I repeat again, I can't say what my personal opinion. My personal opinion is, for instance, that static problems are very far to be trustworthy, of course, but there are there in the literature, and there are important people working in this thing, and who said that about the Albers paradox. This was why there can be an Albers paradox in an infinite universe. There are basic texts of 50 years ago or so already discussing these questions. Certainly, you have to use non-standard physics, non-standard terms, maybe some tricks that I do not agree, just to try to solve a problem with introducing another problem, adding another ad hoc. But there are ways to solve all these things.
Let's wait, Paco.
I have not. I have said that there are big structures and people discussing that there are big structures. I know that there are. Okay, okay, it's okay. It's okay.
And we just got 70,000 euros from the government to model that travel project. We have to go on that right now here.
These papers are published in APJ, Astronomy, Astrophysics, Smallly Notices. If they are published, it's because they have passed some filter. I'm not going to defend. Oh, no, of course, no, but we have to discuss them. Not neglecting them and say they are rubbish. My papers are good, and those papers are rubbish. No, this is not a scientific method.
Well, no, well, anyway, I think we should just, this discussion can take forever. I was just wondering whether there's anyone else in the room who would like to raise his or her hand and ask any question. Right? Yeah.
Thanks for the talk. You highlighted the importance of the data taking or the analysis of data. And I was wondering if you have, how happy you are with the current strategy to take the data to do these surveys, or do you have some alternative in mind? And I was wondering, because for instance, in the dark energy survey, we were not just producing data about dark energy, but asteroids, dwarf galaxies, and a number of other things. So there are synergies. Even the flagship goal is dark energy or dark matter.
Sorry, repeat again the question. The last, I could not hear the last.
Well, basically, just if you have some alternative strategies in mind about the data taking process, the surveys, or you would do it differently to discover alternatives or something.
If I have any proposal for testing the dark energy, or
yes, if you were in charge or even some funding agency to design the survey strategies for humanity in general, would you do something very differently on?
There are many in the literature. No, I have not. I will have to think about it. If I want to be original, first, if I want to be original, I have to revise all the literature. But there are plenty. One thing is clear, possibly it's not an argument enough, but the thing that there are some arguments in favor of the dark energy, and the thing that there are already literature, and I'm talking about professional literature, professional papers with values of omega lambda, which are not 0.7, and even with, or the idea, what I have shown before about the supernova, they explain perfectly the supernova, the difference of magnitude without introducing dark energy. Well, this for me are respectable. I'm not 100% sure of these papers, but they are. They should be put in some level in the discussions. The problem is not finding a new test, a magical test that gives a definitive solution forever of who is right and who is wrong. Now, this is an eternal race. Just I make a prediction. If the prediction works, it's okay. If the prediction does not work, I will make a correction ad hoc. Then, if the prediction is very against to my model, I ignore it and I say they are bad scientists because they don't take into account this effect. It's more it's something beyond science, I think. It's my impression, but I might be wrong.
You already asked.
Just a comment that the people who works in observational data knows that we have a lot of systematics that we have to analyze before to start to talk about new physics. But it is something that we call ego in the community, in the scientific community. And for example, as you show here, maybe it exists an evolution in the supernova type 1 with the age. But before to find that evolution, we change the cosmological model and we put dark energy, for example. And something similar is happening right now with the James Webb data that we know that there is in the calibration data and all these things. But before to analyze that systematics, the people start to know, new physics, the cosmological model is grown and all these things. And I think that this is the ego.
I agree. I agree. And this is one, I have been observing many individuals, scientists that either doing orthodox cosmology or heterodox cosmology. And I agree that there is a lot of egos in this independent alternative cosmologies. But this is part of the game. In the end, of course, there is a psychological process behind, but we cannot say your theory is not good because you have a big ego. No, you have to say your theory is not good because, and go to the scientific details. Ego, everybody in more or less has some ego. Some people has ego of being considered as somebody, a hero alone, and other people have the other psychological trend, which is belonging to the group. There is most of the scientists do not have independent ideas, not because they are stupid, just because they want the conformity. They want the consensus, and this is also something dependent on the psychological. So sure. I'm totally sure that if a psychologist come here to analyze how the science works, can write many PhD theses about the mentality of the scientists, because of course these elements are there. The ego on the one side, people who try to be original, and on the other side, the conformity on the other side. And both are elements of science, yes, but we are humans, we are not machines.
Before I pass the mic back to Paco, I'd like to say one thing. Just as a cosmologist and as a member of the community, my experience is just the opposite of what you have said, right? You have said generic statements about the community, sociological statements about us, that we follow the leader or we follow the crowd, or that, and that there are no independent thinkers, so that there are no people challenging the model. In my 20 plus years of experience, I've experienced a couple of occasions where there seemed to be some evidence for breakdown of the theory, and people were enthusiastic about it. And if Planck, as an experience in Planck, the Planck collaboration, if we had found something really odd, weird, we would have loved it. My experience in the community is that if the model, for whatever reason, breaks down, it would be seen as extremely exciting by us, because we just don't want to converge to this boring Lambda-CDM model, right? And in my experience of all the talks about cosmology that I have seen, I've always seen as a first principle our main ignorance, our huge ignorance about the constituents of our universe. We claim that we have a model that more or less explains most of the observables, but we don't know what its constituents are. So in that sense, I think that all your statements about generic statements or theoretical statements about the community, I don't share with them. This is not my experience. It's not the community I have worked with in the last few years, right? And then just one more thing. Of course, there are papers. There are papers claiming many things in the literature. They have passed the referee, whatever, but there are wrong papers too. There are very wrong papers. And it takes ages to convince some authors that the results are wrong. And at some point, we just ignore those people who just don't want to acknowledge their own errors. By the way, I know major cosmologists who have recognized that they made a mistake, that they have claimed that non-Gaussianity parameter was huge and it was found to be systematic a few years later. I've seen major cosmologists acknowledging their own mistakes, their own errors in the community. Right? And then, of course, there are technical details. I could tell 1,000, particularly those on the Cmb, on which I disagree. The statement that you have sent, you have just reduced to the temperature anisotropies. There is a huge wealth of information in the Cmb from polarization, from lensing. How can you explain that? But anyway, but this would take forever, right? But you know, I would just wanted to say these words about the community. Right?
Because you keep on insisting on supernova. So of course, supernova are based on luminosity distances, and luminosity distances are standard calendars are based on luminosities. And of course, if you can show that changing in a particular functional form, the luminosity dependence on the distance, you can, of course, also achieve a similar result to an accelerated expanding universe, which can perfectly be a mathematical game, a statistical mathematical game. The reason why, and that's and that paper would not be per se wrong, but the reason why it will not be that much cited is because of the following physical reason. There's a fundamental reason why we believe those are standard candles, and it has to do with physics. There is the Chandrasekhar mass. It's very well known for white dwarfs, and we know how a companion star will accrete onto that white dwarf, and we know how that, because this is modeled with simulations, how that under different circumstances, because there's a fundamental mass for a white dwarf, there is a particular luminosity in the explosion process, and that is the underlying physics why we find it more robust. When there is a study telling me, look, there is a environment dependent, it's not the same as supernova within a spiral arm than outside a spiral arm because it's affected by dust and it will be dimmed. Then I think, oh, this is interesting. And we are all interested about those things. But it doesn't mean that playing around with some functional dependencies, phenomenological papers, most of them, as you mentioned them, doesn't work. MONT works, but it doesn't mean it's based on a fundamental physical theory. And that is the reason why we don't like those papers that much.
But I think you trust too much in theory. Physics is not only theory, physics is not mathematics, it's an observational science.
So I think we are running out of time, so just wanted to make a very brief comment. Well, I have the same feeling as Paco before. So there are many issues that maybe we could try to discuss in more detail. Many things that I believe you are doing a biased selection of results, and there are many results, particularly in the topics of expansion, that are omitted.
A very short talk.
But I mean, I think probably the most important point of feeling that I have after listening to the presentation is similar to what Carlos was stating. So you started a few slides before when you were listing the points that the community assumes and is not questioning. So you were citing the different phases of eras of the cosmology. And then you came with a list. Yes, so next one. Exactly. So you in period 6, lack of discussion of the fundamental ideas, and then in the next slide, you start in the following slide, you start with a list of topics that are, in your opinion, are not questioned. In my view, and it is the same feeling that Carlos had, these are the topics in which the community is working nowadays. So everyone is questioning these things. CP violation, it was, I mean, you know, there was a Nobel Prize in 1980 because of the discovery of the CP violation in the K-meson decay, and it's one of the hottest topics in particle physics. Inflation, there are many people questioning inflation. Some of the founding fathers of inflation, Steinhardt, for example, they are now proposing alternative ideas that will be tested and measured with the coming experiments. Non-Barionic dark matter, and many people in the community working in different models, astrophysical models, for example, primordial black holes are possible explanations for this. And dark energy, I mean, Paco was mentioning people working in modified gravity theories. I think this is one of the hottest topics. I mean, if you go to the list of projects that are assigned, for example, in year 6, many of them are devoted to these issues. So, I mean, the list that you were putting there is precisely, I think, the list of topics that the majority of the community is working on nowadays.
I agree. Yes, I mentioned here that there are some people working on the variations. Yes, even with inflation, without inflation, with different types of inflation. But the problem is just going to the fundamental ideas. The problem is, okay, I would like to touch this and modify this or the formation of the galaxies, but they don't want to touch the basic idea because they consider it like a taboo. Or
is it your experience, really? Is that your experience? Have you talked to how many cosmologists? I mean, my experience is that people are open-minded. People want to test the model. Like, if a cosmologist finds that the model is overly wrong, that is a huge failure, people are for that. I mean, he would be very happy. Like, we're expecting, you know, cosmologists are hoping to find some breakthrough, something that departs us from this boring Lambda-CDM model. To the extent, like in dark energy service, which is one of the latest cosmological service, there's a huge effort, huge work team trying to do in order to design how to set up blinding analysis, right? Like blind analysis, not to be biased by our, you know, our idea of what is the value of the parameters that we should be getting. And they have built up a huge machinery that we call paranoid in order not to be biased by previous results from other experiments or other collaborations. My experience is that people, I mean, our obligation as scientists is not just to see whether we fit a parameter or not in the model, is to test the model itself. And the motivation behind most surveys is actually testing the model. You know, and many of us would help, you know, if the model breaks down for whatever reason, it would be great for us because it would, you know, it would give us more reasons to think about and to scratch deeper into nature. But I mean, this conformism, this following the theory, inertia that you have blame on us, I personally have not seen it, right? We want to test the model, and this takes a lot of work, a lot of data, and a lot of careful data analysis. But of course, we want to test the model.
I'm half in agreement with you, half.
Just very quickly, I don't want to get inside the discussion because it's very long and we are finishing the time, but I don't agree totally with what are you saying, Carlos. I remember, and correct me, Andras, some times ago, did a presentation about the void. I don't remember exactly all the particular in the discussions, but he only touched the point that there could be some problems in the Lambda-CDM model, and mostly of the room raise up. How are you saying about it? So there must be some problem. There might be some systematic. There might be some measured problems. So I agree that many people are very open mind, but sometimes yes, there is some frictions when you are trying to going to go to change the mentality in to change something in the Lambda-CDM model, in the standard model. So it's true that there is, so everybody, I think everybody is open-minded here, we are scientists, but there is always there is some friction into left the old model for some new. Okay, we are inside, we are all open to search for every new things, but there is a big column that it's difficult to abandon. So it's you are right, but not so totally right.
I'm sure we have, we have. Maybe you want to answer. I don't know, Martin. Just to give you the last word before I wrap up and I close the session.
No, your point of view is more or less what I think. I agree, of course. Cosmologies are many, are thousands. There are many individuals of different types. And when we make descriptions, we make average descriptions. There is some resistance of big changes. I understand why it is that. So of course, when you have a theory that more or less works, the people is reluctant to make big steps until it is totally necessary. This is how science works. So it's something human, I would say. But on the other hand, it's a pity sometimes that there are no place for some kinds of ideas that are sometimes are mocked. Or when you mention some idea, and for instance, when somebody mentions, oh, but how do you mention this idea of the static universe? We already know from 50 years ago that it was totally solid. Well, possibly you know, but I don't know. Explain it to me again. We should insist again in repeating again the explanation. And the point of being here is not being dogmatic, neither in one side, neither in favor, neither against. The point is being scientific, and being scientific is discussing ideas. I agree with you that there are many scientists that are open to discuss ideas, and they are eager to produce new results that throw to new physics. But we have to agree that there is some in the publications, in the reference system, there is some resistance for the novelties. Something. At least you have to recognize that there is something.
To some extent, I personally agree. To some extent. Okay, people. Thank you, everyone, for attending such a long meeting today. Thank you, Martin, for triggering this discussion. See you on Thursday then.